Hello class, this is our normalization session here, so I guess we'll go ahead and jump right in and get started. Hopefully you read the PowerPoint before this and we're able to digest some of it, so we'll go ahead and let's open it up and start from there, okay? Alright, so normalization is the elimination of redundancy from our database. And what does that mean? Well, basically it means that we will not have to, if we have values in table A, that means that we won't have to repeat those values in table B, table C, because you can see how, see why we call it redundancy in that case, right? We have to repeat ourselves over and over, okay? And this can cause other problems as well. Now, this brings us to our second point. Why do we normalize? The redundancy causes problems, and they're called anomalies. And we'll get into that in just a moment, but we'll see a few examples of the problems that this causes. Now, we do have a process that we follow when we normalize. We have it's kind of a stepwise process. As you get better with it, you'll be able to do it kind of by the seat of your pants, but there is kind of a methodology to follow. We'll see that in a bit, all right? And, we're always going to normalize. If we have more than one table, we need to look at normalization, okay? It doesn't do us much good to have unnormalized tables, and there are several reasons. Again, we'll see this here in a bit. So we'll go ahead and jump right in here. All right, now, going back to our problems, these anomalies, they can be classified into three major types, and they're called update, insert, and delete anomalies, okay? And this basically can have incomplete or can cause overzealous, updating, inserting, or deleting, beyond that which is desired or not quite up to the point of that which is desired, okay? So normalization is done from a high level. We can think of it as decomposition. We take these tables and we break them down into smaller tables, okay? The smaller tables help us keep our data separate so that we can join this data and so that we don't have to repeat this data so much, okay? And this way we have much less risk of, altering or even deleting, things we don't want to, or, missing some of this data, okay? All right. So, we have the concept of functional dependencies when we're talking about normalization. Now, a functional dependency is pretty easy. It's, if you look at it, all the symbology, it may seem a little difficult, a little abstract, but it's really not. A functional dependency is basically a definition. So you can think of it as, given the value of A, I can tell you what the value of B will be. Okay, let's think of a table where we have, let's say, students. Say we have a student social security number and student name and student address. Well, given social security number, I can certainly tell you any given student's name or address, okay? So that's a definition of a functional dependency. Social security number will define name or address, or we can say name and address are dependent on social security number. So you can see the symbol is kind of an arrow there, defining data to dependent data. This is pretty straightforward here, okay? And here's an example here. So if we have a table, business, we have our primary key, tax ID, okay, and we also have business name, business address, and business phone number. So this is the same thing. You see we have an identifier here, tax ID number, that will allow us to obtain name, address, and phone number for any given business as long as we have the tax ID, okay? So this really isn't rocket science, okay? It's pretty straightforward, all right? So you see we have our set notation here. Don't let that fool you, okay? So we can kind of group these three together. Instead of saying tax ID number defines name, tax ID number defines address, tax ID number defines phone, we can say tax ID number defines, within set brackets, name, address, and phone, all right? And I just want to head further within our example. We have, car, VIN, make, model, color, okay? Given the VIN, you can definitely find the make, model, and color of the vehicle, okay? The VIN actually has built in all these attributes, and then it has a checksum at the end. But definitely given the VIN, I can give you any identifying information we need from the vehicle. And you'll see here I didn't write it set-wise. I just kind of separated the dependencies out here so that you could see that it's the same. You can express them both ways. All right. Now, model does not define VIN. You know, given the model, if I tell you my car's a Buick, you certainly can't tell me the VIN. Okay, so this does not apply in reverse. Same with color. You know, if you tell me that the car is green, I cannot tell you the make. Okay, I can't tell you whether it's a Buick, a Ford, a Honda, anything like that. Okay. All right. You know, if you give me the model, I can probably tell you the make of it, but that's a little exception. That's not technically a functional dependency. Okay. You know, I can probably guess the make given the model, but that's not a dependency in formal terms. All right. So going back a minute to anomalies. Okay. So here we have an unnormalized database. We say zero normal form also. Okay. Now we kind of have all of our attributes crammed into a single table here. So we have what? We have ISBN, name, pages, publisher name, publisher address, author social security number, author name. So you can see we have a lot of, you know, these are kind of candidates here for being their own attributes, you know, author, publisher, okay, and book. All right, so we kind of crammed them all into one table. All right. And we just want to delete one of the books. All right, we want to get it out of the database because we don't have the book in stock, or it's not needed, or discontinued, or what have you. So, you know, let's say we just go ahead and delete this book. All right, and you see what happens here. We delete all other kinds of information. So we lose all of our information about the publisher. Okay, we can lose all our information about the author. All right, so you see what happens. We have to repeat data entry. And each time we repeat data entry, we run the risk of an incomplete or an incorrect entry, right? Because, you know, we have to depend on people typing these things in and people to make mistakes, okay? So we could have eventually a lot of different, you know, let's say somebody thinks Elf is spelled with 2 F's, all right? Another person thinks Todd is spelled with 1 D, all right? Or they mistype author social security. So then our data kind of becomes corrupt and invalid. Any queries that we issue will miss things. All right, or you know, if you incorrectly modify a row and it happens to match another row, then you kind of got additional data that really shouldn't match that does in the future. All right, so you can see this is a deletion anomaly. Okay, when we axe info that we really don't want to, or that we don't need to. All right, delete, insert, and update. So here's the second insert. So you know, if we want to put info about a new author in there. Okay, let's say, you know, I have Kenny G here, he's a musician, but we'll say he's an author, all right, and I've got a social. We want to put him in the database, but, you know, as is, this table, we kind of have to insert a whole bunch of null values, which is silly, right? So you see, I have to null everything out, and then enter Kenny G and his social security number here, all right? Yeah, and as I said before here, you know, if you have to enter a lot of data, we're depending on people being perfect, which they aren't. People are human, they make mistakes. So this mistake, the chances of mistakes anyways, grows, you know, linearly with the amount of data that you have to increase. Okay, so you can get typos, and then you'll have corrupt data, which is bad, bad, bad. You know, you got garbage in your database, and what's the saying? Garbage in, garbage out, right? If you got garbage in there, it doesn't matter. You know, it's all garbage. Okay. And last, update. All right. So, you know, when you're normalized, you can have partial or incomplete updates, or even update rows that you don't want to. All right, and the example I have here, excuse me. So let's say that Joanne Smith changes her name. All right, and see, I have a misspelling here. I misspelled her name, okay? And so if she gets married, let's say, you know, and this is just one example here, you know, this is one row. Of course, if we have to enter her name in several times, we're going to have, you know, higher chances of having inconsistent data. But you can see what can happen here. We can miss some of the rows, okay? Because if some of these rows are inconsistent, we run, you know, well, we don't run the risk. If we update it, it will miss the row, okay, and then we have inconsistent data. All right, so that's an update anomaly. You know, when you miss updates, or even get more updates than you really want to. All right. That's an example of an updated anomaly. So now, kind of back to pure normalization here. So, I said before that we do this stepwise. We do. We take an unnormalized database, and by applying our different rules through our steps, we can go higher up on the normalization chain, on the normalization totem pole, I guess, if you want to call it. All right? They go from, unnormalized up to 6 normal form. Really, 6 normal form is purely academic. 4th and 5th normal form, they arguably have their uses. And then below 4th normal form is voice cod normal form, and even that's a little beyond the realm of most databases, okay? But 3rd normal form is what you need to know right now, okay? If you go on to take a grad level class, or if you go on to be a database architect, you'll surely know more about normalization beyond 3rd normal form. But for right now, 3rd normal form is going to suffice, okay? That suffices for most applications, all right? And there's a handy little mnemonic here. A mnemonic device is something that aids memory, okay? And the mnemonic here, if you kind of think of the famous quote, oath, the key, the whole key, and nothing but the key, so help me God. Kind of reminiscent of what the truth, the whole truth, and nothing but the truth, so help me God, okay? So you have the key, the whole key, and nothing but the key, so help me God. And, Codd is Edgar Codd. He was the, the inventor of the relational database model. Okay, so just remember that catchy little saying, and we'll see this here in just a second. All right. So 1st normal form is the key. All right, so make sure there's a key. Easy enough, right? So make sure that there's a primary key that prevents repeating groups, okay? Now, what's a repeating group? We can think of a repeating group as a set of values for one single row in the database. So let's say we have, think of it as a multi-valued attribute that doesn't get broken out into a separate table. Like, let's say we have store, and we have store name and phone numbers, okay, in a table. Well, you can have more than one phone number per store, so that means that we would have a set of values for our phone number, and that's not good because then we have repeating values. We are non-normalized, and this is bad news, okay? So that would mean 0 normal form. Let's see, what do I have here? Our book databases are normalized because of the repeating groups and the non-PK fields, the author and publisher. Right, so if we go back here, yeah, okay, so you see what we have here. We are unnormalized because we have XYZ Publishing, 123 Oak, a couple of times here. Then we can have it really, if we like this publisher and we have 100 books by them, we'll have a whole heck of a lot of repeating groups, right? Same with author. We'll have a whole lot of, George Harris's, if we have a whole lot of this, if you wrote more than one book, and we stock more than one book. So that's a problem, okay? And this leads to anomalies. Yep. All right. Okay. And yeah, that's an example of redundancy. All right, so there are kind of 2 techniques to go from unnormalized to 1st normal form. We can either flatten the table, which means including all the repeating groups in the primary key. Okay, if you think about that, that will prevent this problem. Okay, because it will. Hold on, we'll go back here. We'll give you an example. I know there's a little shortcut here to go back. I don't know. Let me see. Is it? Yes. Okay. So it's just the back arrow key. Anyways. Sorry, I lost my place here. Oh yeah, flattening the table. All right. Okay, so we can, in this case, we would include the primary key. Let's say, ISBN would be a good primary key here, right? Since it's a book table. So we'll say ISBN plus any repeating attributes. So that would have to be, let's say, publisher name, publisher address, author social security, author name. That will ensure that all rows have unique values, okay? But that doesn't really help us a whole heck of a lot, right? We still kind of have a lot of duplicates going on. So really, that satisfies 1st normal form, and that we don't have technically repeating groups, because repeating groups would be values that repeat outside of the key, okay? So yeah, flattening the table technically helps us, but it's not a really good first step, okay? It's just worth mentioning, all right? Or and here's what we like to do. We break the repeating groups out into their own tables, okay? So we decompose, okay? We decompose according to the functional dependencies. There we go. All right, so yeah, here's the example right here. Sorry, I forgot I had put this. All right, so we can flatten it. So here's all of our garbage inside with no primary key, and we can make it just a book table, okay? We'll say ISBN is our ideal primary key for book, and then everything else that repeats, I said these 4 attributes will be part of the key, all right? So as you can see, we have name and pages, okay, which will not repeat. Technically, we could have more than one name, but it's not for the same book, so it's not technically a repeating group. So this way we won't have repeating groups, right, outside of the key, but we still have a whole lot of duplication, so it's not, it's not an ideal first normal form step, okay? And besides, this technique really isn't good outside of first normal form, okay? Or we can decompose it. So what we do is we look at this thing and we say, okay, we have all of our book values, right? These 3, name, ISBN, and pages, are going to be our book values. So we'll make this its own separate table because ISBN defines pages and name. Okay. Does ISBN define publisher name? Well, I can certainly give you publisher name given ISBN, but it's not really directly related to ISBN, so I wouldn't say that that's really a functional dependency. Okay. We have our logical group over here, publisher name and publisher address. Now these, yes, are going to be grouped together, okay? So they logically group together, and I say, given publisher name, I can definitely give you publisher address. That is a functional dependency, clearly, okay? So I'll break this off into its own little table, all right? And over here we have kind of a third logical entity here. We have author, social security name, and author name, so we're going to have an author, okay? Social security number definitely definitely defines author name. Author name is dependent on social security number. So voila, here we have it. So we have book, ISBN, and name. Oh, actually, I should have included pages in that. I slipped up there. Publisher, so we have publisher name and address. Of course, publisher name is the primary key. It defines publisher address. And the same with author, social security number and author name. So that's an example of decomposition. We break down according to functional dependencies, all right? Now, for the functional dependencies, we'll have to pay attention to logical grouping, all right? There we go. And this is the explanation, okay? So we see ISBN defines name, publisher name defines publisher address, author social security number defines author name, all right? So here they are. Here are the FDs on the right, and then the the resulting tables on the left. All right, second normal form. Remember the key, the whole key, and nothing but the key. So here's the whole key, okay? Everything, all the junk outside of the key has to depend on all the junk inside the key, okay? So kind of to remove all the little pedantic, I guess academic little circles I can make with this. Does all the junk outside of the key depend on all the junk inside the key? If that's the case, it's in second normal form. The key, the whole key, okay? So everything outside has to depend on the whole key. All right. So, for second normal form, we have this concept of transitive dependencies. Now, a transitive dependency is kind of like it sounds. This would be a case of A defines B and B defines C. C is transitively dependent on A through B. Okay, so that is a transitive dependency. That's not a problem in second normal form. Okay, we can have an attribute that defines another attribute, which defines another attribute. As long as the first attribute is attributes represents the whole primary key, then we're fine. We can have transitive dependencies in second normal form. But it's important to introduce this concept now before we hit third normal form. Okay. Now, flattening is not an option here. That was only 0 normal form to first normal form. To convert from first to second, we will again decompose. Okay, and that's kind of the name of the game here with normal forms. And you'll find a lot of the time that when you choose decomposition as your first step, which you probably should, you will find that you are far beyond their first normal form. Sometimes you're in second normal form, third normal form, even up to fifth and sixth normal form. Okay. Okay, so you see here why flattening isn't a good idea because really if we flatten, we kind of violate second normal form and beyond. So we want to avoid that, but it's worth mentioning for academic discussion. Okay. All right, so to convert to second, we break out the corresponding PK. The PK component parts of the non-key attributes in any table are dependent on the whole primary key. And again, we can have transitive dependencies. All right. So this is just to give you an example here, because when we decompose, we see that we're in second normal form and beyond, so really that wouldn't have done any good. So what I did is I took the example of when we flattened as our first step, because here we have an example of a table that's in first normal form and not in second normal form. Okay, the key, the whole key, and nothing but the key. You know why it's not in second normal form? Take a look at it for a sec. Go ahead and pause me if you want, and I'll be waiting, I promise. Okay. You see it? Here we have name, okay, and pages is the junk outside of the key. Okay, name depends on ISBN. ISBN defines name. Given ISBN, I can tell you the name of the book, definitely. And I can tell you the number of pages in that book, right? Okay? So we depend on the key, right? Okay? But we don't depend on the whole key because look, publisher name, publisher address, author, no. You know, given author name or author social security, I can't tell you the number of pages or the name of the book. You know, that's just kind of a ridiculous assumption because an author can have more than one book, right? And the same with publisher. You know, heck, a publisher can have more than one book, so that doesn't apply. So we're violating second normal form here because all the junk outside the key doesn't depend on all the junk inside the key. All right? And what do? We decompose it. Remember, how do we decompose? We decompose according to functional dependencies. You saw this earlier, so you know, it's pretty easy. Here we have, you know, again I missed pages, so we should have, you know, name and pages here, and you know, name, author, social security number, and author name, right? Because we see the functional dependencies over here. All right, and given ISBN, I can tell you name and pages. Given publisher name, I can tell you publisher address. Given author social security number, I can tell you author name. All right, easy enough, right? All right. So here we go, third normal form. The key, the whole key, nothing but the key. Okay, nothing but the key. So here, transitive dependencies are disallowed. Okay, for third normal form, we cannot have transitive dependencies. We can't have an attribute which depends on another attribute, which depends on the primary key. Okay, even if it's the whole primary key, we're still violating third normal form. Okay. Okay, so really to convert from second to third normal form, again, we decompose. Okay, so we will take this last attribute, you know, this vicariously dependent attribute out into a separate table. Okay, and here we have an example. Okay, so here's an example of a table that's in second but not in third normal form. Okay, and I hope this clears it up. So let's say we have a business. We have our tax ID number. That's a good primary key, right? We have a name. We have its, you know, where it's located, you know, let's say the municipality, and we have our tax rate. Now, the problem here is that let's say the municipality is what charges the tax. So that's going to give you the tax rate, right? So tax rate is dependent on location municipality, and location municipality, let's say, is dependent on tax ID number, because given tax ID number, I can tell you location municipality. So we have A defines B, defines C, where A is tax ID, B is location municipality, C is tax rate. So there you see that's our transitive dependency. Even though we depend on eventually depend on the whole key, it's still through location municipality when we're talking about tax rate. Okay, so that violates third normal form. We're in second but not third normal form. Okay, and you see here we have here I pointed out. Tax ID number defines location municipality, and it defines name, and it also defines tax rate, but through location municipality. Okay, so then you can see here I have our transitive dependency kind of written out symbolically. Tax ID number defines location municipality, which defines tax rate. All right, so we just kind of break this out. So here you go. You take location municipality, put it into a separate table. And since it defines tax rate, you also go ahead and put tax rate in there. So we break these tables out according to functional dependencies. Okay. Okay. So, as I said earlier, many times when you choose decomposition as your first step, you'll already be in third normal form and beyond. You can just go ahead and celebrate. You don't have to do a whole lot more beyond that. A lot of the time, you'll always have to check your rules. Okay. And of course, like I said, there is life beyond third normal form. We have Boy Scout normal form, fourth normal form, fifth normal form, and sixth normal form. Sixth is purely academic. Fifth and fourth have their uses, although they're limited, as does third, okay? As does Boy Scout normal form. Third normal form is usually sufficient, and that's all we're going to study here. You may learn more about it later. Just be aware it's there, okay? All right, so and just some little interesting tidbits here. You don't always have to normalize all the way up each and every time. Many times, depending on how many smaller tables you break into, these joins can get computationally expensive, right? Even though you have the internal optimizer and modern database systems are pretty good about that, and memory is cheap, right? And GPUs, what Moore's law says, we double processing power every 18, 24 months, I believe. You still processing power and computation time is an issue, okay? So if you break down too much, if you get a whole heck of a lot of small tables, you may find you're suffering. You have performance penalties anyway. So, the popular saying is, normalize until it hurts and then denormalize until it works, okay? So just kind of be aware. You don't always have to normalize. You don't always have to look and make sure you're in, sixth normal form every time. That's a little overkill. So you do want to go all the way up, check it out. Check out your performance, and then you can scale back and denormalize as necessary. All right. Again, for this class, third normal form is sufficient. That's what we want to ensure that we get up to. We don't back off in this class. We just this is theory only. All right. So I got some examples here, and we'll just go ahead and run through these really quickly. We'll kind of do these on the fly here. All right. So we want to check our we kind of want to check our normalization forms here. So here, let's say this is a database, this is a database, this is a database, and this is a database, or Schema if you're an Oracle guy. Okay. So what do we have here? What normal form is this in? If this is just a table consisting of one database. Okay. We have car, then make, models, features. So you should go ahead and pause me here and see what you think. Okay. All right. Well, okay. Is it in first normal form? The key, the whole key, nothing but the key. Is there a key that prevents repeating groups? We have a key. All right. Do we have repeating groups? Oh, you bet. Look at all these features. You can have power windows, AC, tilt. Oh gosh, I don't know. Built-in MP3. So you can see that we violate first normal form because we have repeating groups. Features will repeat. Okay. Just kind of think of it as this way. Let's say all right, so there's the example that kind of proves it. That's the bare minimum needed to prove my point. Or you can also write it as you can write it in set notation. And there you go. So we kind of proved that we do have a repeating group there. All right. So zero normal form, right? Zero. And here we go. All right. I kind of broken this down. So let's see. Now we have car, VIN, make, model. Okay. Car features. We have VIN and feature the key. All right. Good. So are we in first normal form? Do we have a key that prevents repeating groups? Yeah, because I can only have one make and one model per VIN. VIN defines make and model. Okay. Car features. Oh yeah, I got the whole darn key here. So if you have the whole key, you are on a 2 attribute table. You're automatically all the way normalized. So we're perfectly fine there. There's nothing outside the key that can repeat because there's nothing. There's no non-key, right? Okay. So you have a key, the whole key. Okay, so does all the junk outside the key depend on all the junk inside the key? Yeah, we said make and model depend on VIN. In other words, VIN defines make and model. You know, given the VIN, I can tell you the make and model. And here, this is a non-issue. Again, we have all key, and we're only 2 attributes. Okay. All right, so we're in second normal form. The key, the whole key, nothing but the key. Okay, so here, yes, we're in third normal form because make and model depend directly on VIN. You know, in other words, model doesn't really depend on make, which depends on VIN. You know, given model, I can probably tell you make, but that's not really truly a pure functional dependency. Okay, because we could probably have more than one model name, like let's say Fiat has a 500 and Chrysler has a 500. I know they have a 200 and 300, but you know, let's say for argument's sake that they, you know, that there is some repeating. Of course, Chrysler owns Fiat, if I'm not mistaken, or maybe it was the other way around. But you get my point. Okay, so here we are in third normal form. We're all the way up, as far as we're concerned, anyways. Okay. All right. So next example. Okay, take a sec to look at it. Tell me what you think. Put me on pause, whatever. Okay. All right. So we have retail chain, tax ID, chain name, retail store, tax ID, store number. Okay. Address, and store employees. Tax ID, store number, and then we have our employee stuff. Okay. Do we have a key that prevents repeating groups? Let's see. Chain name. Yeah, chain name won't repeat. Okay, so for each tax ID, let's say one tax ID will belong to Walmart, one tax ID will belong to, I don't know, Best Buy, one tax ID will belong to, geez, I don't know, Office Depot. Okay. All right. So here, yeah, you're not going to have more than one address per store. Okay. So we have tax ID and store number. So we have a store belonging to a chain which has an address. Right. Good. Okay. Store employees. All right. Let's see. Do we have repeating groups? Can we have more than one employee per store? Oh, you bet. Darn. You bet. Okay. So we're in zero normal form here, right? So how will we remedy this? Okay. Well, what we should do, right, we decompose. Okay. So in this case, we said these are okay, all right? Oh, and I should also mention here, we have a nested repeating group. Okay. Because not only do we have more than one employee per store, each employee can probably have more than one position, right? You could be a stalker, a clerk, a supervisor. That's probably okay. I would imagine, anyways. It seems to make sense. So we kind of have a nested repeating group there. So what we can do is kind of break out employee. Okay. Now, if I were to do, let's try this. I could try this, okay? I could say, hey, all right, we have a multi-valued attribute. Let's say employee has more than one position, okay? So what we do, we put the primary key in the table along with the multi-value attribute as part of the primary key. So that looks good, right? Well, okay, but the only problem is we can't identify the employee with the store, can we? So we have to do something like this, right? Sorry. Okay, but the only problem with this is that we still have a repeating group because, all right, we've identified employees with a store. Good. Excellent. Okay. We can still repeat. So we'll still have the same employee ID number here, repeating. Okay. So we'll take this last one, employee position. Okay. Now that we've identified an employee with a store, we can break him out. See, this way we can still join to the employee position if we want. So, like, let's say we, I don't know, let's say we want the names of chains with employees who have employees that are janitors. Okay, so we could say something like, this is kind of shooting from the hip here, so bear with me just a sec. Alright, we're joining on primary key. Okay. So I see, you know, I have tax ID here in retail chain, and I can join it to employee, directly to employee. I can skip over retail store, right? And then I can join, here we go, employee ID to employee ID. Always join primary key to foreign key. Okay. So there we go. So we can do something like that. You know, this way we can join all the way out. Okay. Okay. And all right. So here, let's see. We have another example. We have schools. Okay. School number. We have school name, subjects taught. All right. School students. We have school number, student name. Okay. And then we have students GPA. Okay, so let's see. Okay, so in first normal form, is there a key which prevents repeating groups? Now, I can tell you right away. Well, yeah, go ahead and pause here and see what you think. Try to break it into third normal form. I'll come back. Or you'll come back to me. I'll be here. Okay. So we have, you know, you see here's the violator right here. Okay. Subjects taught. That's a repeating group, right? And what do we do with repeating groups? Okay. We break them off into their own table, which is the primary key of, you know, of the parent table, if you will, and the attribute name itself as part of the key. Oh gosh, what was this? So that's subjects taught. Yeah. Okay. All right. So how about here? School students, student number, student name. Will this prevent repeating groups? Well, perhaps. You know what? We'll say it will. Okay. And we're wrong, because we have students. Okay. So we'll have more than one student per school. Okay. So what do we do with repeating groups? Okay. Student number, name will repeat. Okay. Or actually, the school number part will repeat for different student numbers and student names. Okay. So we break them out into their own. Well, you know, in this case, what can we do here? We can key it, right? Okay. So if the whole thing is all key, then it's not going to repeat. Okay, but notice we have student number and student name. All right, so this is true, right? Student number defines student name. So we'll need to break it off into its own table. And that's so because we have a nested repeating group here. So there we go. We took care of that multi-valued attribute, right? Now for the nested multi-valued attribute, actually we'll just call this student. It's not really nested. Excuse me. I do need on the fly here, so bear with me. Just kind of made these up and figured I'd walk through the methodology here with you and figure it all out on the fly. So, in this case, we don't have more than one student name per number. So it's not really, it doesn't repeat. It's not a nested repeating group, excuse me. But, given that school number, given that, school number does not define student name, I thought it best to do it this way. So here we have our multi-valued attribute, okay, which we know that we break off into its, its own table consisting of the primary key plus your multi-valued attribute. So hence we have school number and student number, okay. And then we actually have our student table here with our student, because student number defines student name, all right. And let's see here. Oh, well, the heck, since I already have student, I can include GPA in here because student number will certainly define student name and GPA. I can tell you a student's name and GPA based on the student number. Okay, so let's go back to the beginning here. We'll do Control-Z a whole lot, and we'll go back to the very beginning. Find it as it was in its original state. All right. There's Control-Y to redo, by the way. It's a helpful tip, maybe. Okay, so what we're going to do, we're going to go ahead and we'll grab all these. Right, so we have school number, school name, subject taught, student number, student name, GPA. All right, so what are our functional dependencies? All right. Given the school number, I can certainly tell you the school name. Okay. I can tell you the subject's taught. And what, given the student number, I know there's more than one, so I'll put it in chat notation here. I can tell you student name and GPA. Okay, so there are our functional dependencies. All right, and it could be tempting just to write these out as is and just say, hey, we have a table that should be school name, the subject's taught, and a table that should be student name and GPA. But we do need to link the two, right? So we kind of have to use our heads as we normalize. All right. If we have a database, we have to link the tables. We have to be able to join all the way and get all of our data. So that's why we have our little intermediary table here. Okay, school number and I actually need to redo all of my previous work, but you get the point. That's why we have our school student table. That looks something like this, since the student number was it was a repeating group. It was a multi attribute. Okay. All right. So I hope this helped clear things up a little bit. It's not too bad. Just keep in mind the key, the whole key, and nothing but the key. So help me God. You just keep in mind the repeating groups are multi-valued attributes. What you've done up to this point, when you followed the mapping rules, you've basically been normalizing without realizing it. If you follow those mapping rules to convert ER diagrams into actual, schemas, you should be in third normal form most of the time. Okay, so you kind of been doing it behind the scenes and didn't even realize it. And this is the why behind it. Okay, this is the how and the why. If you need to create something from scratch, okay, and you want to follow normalization rules, you want to make sure you're normalized. All right. So, you can find tons of examples on the internet. You can find tons of examples to work. Just be careful where you look because not all of them are correct, okay? As usual, if you have any questions, just ask, and I hope this helped clear things up. All right, see you at the next lecture.